Hi everybody, my name is Christoph Stach. I'm from the University of Stuttgart, and together with my three colleagues, Clementine Kritti, Denis Pritztarski, and Bernhard Mitschang, I studied whether blockchains can be reconciled with data privacy laws such as the GDPR. That is, we wanted to find out whether blockchains can be used to store sensitive or private data in a privacy-aware manner. Let me give you a quick example what I mean by that. When you want to share some sensitive data with third parties, let's say this data item with Anna and Bob, then you could send both of them the data item via mail. When now Anna wants to update the data item, she has to inform you that there was an update, and now you have the newest version of the data item as well. However, Bob doesn't know about the update, so Anna has to inform him as well. Yet, if Bob has altered his version of the data item in the meantime, then there is a conflict. So therefore, a better solution would be to use a common data store. When all parties involved have access to the data store, then you only have to send your data item to the data store, in this case a database, and everybody has the newest version of the data item immediately. Yet, if a malicious third party has access to the database as well, then he or she could delete some of the data items or alter some of the data items. And that's where the blockchain comes into play. Instead of using a database, you could use a blockchain to store sensitive data in a secure way. Why is it secure when you store the data in a blockchain? Well, that's because of three characteristic features of a blockchain. First of all, a blockchain is decentralized. So there is not one single control unit who has the central access and central control over the blockchain. Then the data which is stored in the blockchain is immutable, so no one can delete the data. And the data is also tamper-proof, so no one can mess with the data in the blockchain. Well, that sounds great. Where's the problem? Well, the problem is if the sensitive data is personal or private data, then you have to consider the GDPR. And there are some requirements due to the GDPR. For example, when you process private data, then there has to be a central data controller. However, since the blockchain is decentralized, there is no such controller. Then the data subject has also some rights. For example, he or she can or has the right to get his or her data deleted. And this is not possible in a blockchain because the data is stored immutable. Then he or she has also the right to let some data be corrected by the data controller because the data is false or he or she doesn't want to have that kind of information shared via the blockchain. This is also not possible because the data in the blockchain is tamper-proof. And therefore, we came up with a research question: is it possible to design a privacy-friendly blockchain? Here's the outline for the rest of my talk. After this quick motivation, I want to talk a little bit about blockchain foundations. So, how does a blockchain work internally? Then I want to look at blockchains from a GDPR point of view. So, which conflicts arise when private data is stored in a blockchain? Then I will talk about related work, and I'll show you some extensions to blockchains we came up with in the context of this work to solve the issues which we found out are between blockchains and the GDPR. Then I will give you a quick assessment of those extensions, and finally I conclude my talk. So, how can users store their data in a blockchain? The simple answer is they can't. They send the data items they want to include in the blockchain to a transaction pool. Then we need a network of worker nodes. These workers pick up an arbitrary number of data items and create the next block. Yet each worker operates independently. So in this case, in our network with 3 nodes, we'll end up with 3 different blocks. Therefore, the network has to reach a consensus which version of the blocks should be included in the blockchain. When they agreed on a block, then this block is generated and added to the blockchain. But how does this adding works? Well, when we create a new blockchain, then there is this genesis block. The genesis block is the very first block in our blockchain. This consists of 2 parts. First, we have a header, which is not really important in a genesis block, and then we have a data part. And in this data part, our payload is stored. So in our case, the data items. When the first block was created and we create the next block, then the header of the next block, of the second block, is used to link it to the first one. And this happens since we create a hash value of our genesis block. So we store in the red block a hash value of this genesis block and all of its data. With this header, we can verify whether the genesis block was somehow tampered with. So when we change the data in the genesis block, for example, then the hash value of the genesis block also alters. So since we have the hash value stored here, we cannot change the data in the genesis block without changing its hash value as well. So since we know the hash value of the red block, then we can say, okay, with this hash value, we can verify whether the blue block is unaltered. And in addition to the header, the red block has a data block as well. When we now add the third data block, well, we also have a data part and a header. And this header creates a hash value of the red block. So with this header, we can verify the data of the red block. But since the header is part of the red block as well, we also can verify that the blue block was not altered, because the hash value of the red block would have to change if the data of the blue block was altered. So the longer our blockchain is, the more secure our data is as well. And these strings of data are then separated in a network. So we have different nodes, and each node has all blocks of our blockchain. Thereby, not a single node controls our whole blockchain and could change something, but we have a whole network, for example, a peer-to-peer network with different nodes, each containing our original blockchain. So even if we assume that one of the nodes is malicious, we can still make a majority vote, which is the correct version of our blockchain, and so our data is secured. Now let's have a look which of these properties are in conflict with the GDPR. By default, blockchains do not consider how the data which is stored in the blockchain are processed. The blockchain is first and foremost a data store. So there is no purpose limitation. When you have access to the data, you can do whatever you want with the data. Then there is no data minimization, since all data is available in each of the nodes. So each node has a full copy of the entire blockchain and therefore a full copy of all the data stored in the blockchain. Closely related to this is that blockchains are append only. That is, new data is added to the end of the blockchain. However, old data is never deleted. Therefore, there is no storage limitation. Blockchains also do not require the consent of a data subject to process its data. That is, the processing which is done in the blockchain is just storing the data. What happens later on is not part of the blockchain. So the blockchain won't ask for the consent of a data subject for any further processing. As you already seen, the data is stored in a decentralized manner. So we won't have a central data controller because this would fundamentally contradict the decentralized nature of a blockchain. A data subject also has the right to rectification if wrong data is stored by a data processor, and the right to erasure if the data subject no longer wants the data processor to have access to the data. This is not possible in a blockchain because the data in a blockchain is immutable. So we can't change the data which is once stored in the blockchain, because this would change the hash value of our block in which this data item is stored, and therefore destroy our entire blockchain, because all headers of the subsequent blocks would have to change as well. And the problem is that only if all of these technical issues are addressed, a blockchain can support data protection by design, which is also required by the GDPR. These conflicting issues are only an excerpt of all the conflicting issues. For more information, please have a look at our paper. There are 4 types of related work: literature reviews, technical solutions towards a privacy-aware blockchain, administrative guidelines, and legal assessments. The literature reviews show that there is currently no technical solution towards a general purpose blockchain that addresses all the privacy issues I mentioned earlier. The few technical solutions that can be found in literature are dedicated to a certain use case, and they can apply it only in that use case. For example, in the smart cars domain or in a smart healthcare scenario where a lot of private information is included. The administrative guidelines, on the other hand, explain, for example, an administrator how to operate a blockchain in a privacy-friendly manner. Yet, since there are no technical measures how to implement those guidelines, this is a really tough job for the administrator. And finally, the legal assessments come to the conclusion that a GDPR-compliant public blockchain is basically impossible, because there is no controlling entity and such an entity is required. However, in a private blockchain, that is a blockchain that is operated by a certain consortium, this could be possible. And this is the starting point for our work, because we thought about private blockchains and how to extend private blockchains so that they are more privacy compliant. Our first extension is called data purging by encryption. So now let's have a look how data are organized within the block of a blockchain. They are organized in a tree-like structure called Merkle tree. And the root of that tree is the entry point within our block. The data themselves are stored on the leaf level of the tree. So what we want to do here is we want to delete a certain data item. As we've seen earlier, this is not possible in a blockchain because of the hashes we use to connect the blocks of our blockchain. But what we can do is we can encrypt the data, and if we delete the key to a certain data item, then the data becomes no longer readable. By using an hierarchical key management introduced by Weizenegger et al., we can achieve this. So each data item is encrypted with a different key, and then we have a tree-like structure that is mapped to the Merkle tree with different keys. So for example, if I delete the green and yellow key, then the green and the yellow data item are no longer readable. That way we can delete the entire block in a blockchain or only certain data items. Our second extension helps to restrict access to data stored in a blockchain in a fine-grained manner. Therefore, we introduce a new permission model. Our permission rules consist of an accessor, so who wants to have access to data, and a resource, so which data item or which data items are involved in this access. Then the data subject can define a purpose when a certain data access is allowed, and this purpose is identified via the attributes of the accessor. So the accessor not only has his access credentials, but also some attributes how he or she wants to process the data. And finally, we can also add some constraints to our permission rule. So these constraints are described by privacy filters. So how to pre-process the data before sharing it with the accessor. And what I mean by privacy filters, I will describe on the very next slide. Let's assume we want to share these raw data with a third party. However, we want to conceal certain aspects of it. Therefore, we send the raw data to a trusted execution environment and apply a privacy filter to it. There's a repository of different filters available, and the trusted execution environment selects the correct privacy algorithm from that repository. That way, we can have different versions of this raw data. For example, one version where we add some noise, or where we reduce the details of our data, or where we reduce the details to this extent where we only see minima and maxima values. How can we apply these extensions to a blockchain? Very simple, by embedding the blockchain in a trusted privacy control environment. That privacy environment encrypts all incoming data before storing the data in the blockchain. And when a data accessor wants to have access to the data in the blockchain, the trusted privacy control environment decrypts the data. That way, the privacy environment can do some verification of the data, can correct wrong values in the data, and can also delete some data by deleting the respective encryption key. Furthermore, it's ensured that no third party can access the data without using the trusted privacy control environment, because the third party would not have the required decryption key. By means of our extensions, we are able to revise or delete data stored in a blockchain. We can ensure the quality and correctness of data in a blockchain. We can restrict the processing of data. We can reduce the information value of the data. And we can also help to manage the data in a privacy-friendly and privacy-aware manner. Due to their decentralized, immutable, and tamper-proof nature, blockchains are a good means to share data with multiple parties. However, from a privacy perspective, these properties are in conflict with data privacy laws when private data are involved. We've shown that with our extensions, however, a privacy by design blockchain is feasible. For more information on these extensions, please have a look at our paper. Thank you very much for your attention. In the following, you'll see the references I used in this talk.